Hello friends, in this lecture we will derive an important expression for the signal to quantization noise ratio at the output of the reconstruction filter in a delta modulation receiver. Consider the problem for a sinusoidal modulating signal m of t equal to a cos omega mt, where omega m equal to 2 pi fm. Show that the maximum output signal to quantization noise ratio SQNR in a delta modulation system under the assumption of no slope overload is given by SQNR at the output equal to 3fs cube upon 8 pi square fm square f sub capital M, where fs equal to 1 by ts is the sampling rate and f sub capital M is the cutoff frequency of the low pass filter at the output end of the receiver. So what are we supposed to do in this problem? What is given is a sinusoidal signal and no slope overload condition is to be followed. We know that, as we have derived in the previous lecture, that for no slope overload there is a limit on the maximum amplitude of the sinusoidal signal, and that maximum limit is A max equal to delta by 2 pi into fs by fm. The corresponding maximum signal power will be P max equal to, now we know that for a sinusoidal signal A cos omega t, the power, average power is A square by 2. So the corresponding maximum power will be A max square by 2, which is equal to delta by 2 pi into fs by fm whole square by 2, and that is equal to delta square fs square upon 8 pi square fm square. So this is the maximum signal power. Now we need to look at the quantization noise power, because we'll talk about the signal to quantization noise power ratios. Now we know that the quantization noise power for a DM delta modulation system, denoted as E of Q square, this quantization noise power delta square by 3 is uniform up to the sampling frequency fs. So this is uniform over the frequency band up to fs. Now in the output of the receiver we employ a low pass filter as a reconstruction filter, and the cutoff frequency of that low pass filter is given to be f subscript capital M. So because delta square by 3 is the noise power throughout the frequency band up to fs, but the low pass filter will curtail the frequencies beyond fm, so the corresponding noise power will also not appear at the output of the filter, and the noise power that will appear at the output of the filter will only be the one which is allowed to pass through the low pass filter with cutoff frequency fm. So since delta square by 3 is the noise contained by fs band, so since fs band contains the noise power delta square by 3, so the fm band, which is the cutoff frequency of the low pass filter at the receiver, will contain the noise power given by delta square by 3 fm by fs. Let us denote it by NQ, the quantization noise power that appears at the output of the post-reconstruction filter. So the signal to quantization noise ratio, therefore, signal to quantization noise ratio at the output of the low pass filter will be equal to the signal power, which is P max as we already computed, upon the noise power NQ, and P max is equal to this expression. Let us put it here. So delta square Fs square upon 8 pi square Fm square divided by this NQ, which is delta square Fm divided by 3Fs, and when we simplify it, it works out to be delta square and delta square will cancel. This 3Fs will go up, so we get 3Fs square into Fs, so Fs cube upon this 8 pi square Fm square F sub capital M. So this is the SQNR at the output of the low pass filter in the DM receiver, and because here we have considered the maximum signal power, the corresponding SQNR is the maximum possible SQNR. This is an important expression which can be memorized and directly used for solving problems. Note that sometimes in the problems they don't specify the cutoff frequency of the low pass filter used as a reconstruction filter in the receiver. In that case, we can consider F sub capital M to be equal to F of small m. So let me just make a note of it. Note, if the cutoff frequency F sub capital M of the low pass filter at the receiver output is not specified, we can consider F sub capital M equal to F sub small m. In that case, the SQNR at the output of the low pass filter is equal to, putting Fm equal to F small m, we get Fm cube here. So we get the expression as 3 by 8 pi square into Fs by Fm. So I hope this derivation of this important expression for SQNR is clear to you. In the next lecture, we will apply this expression in solving a couple of problems. Thank you.